Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we continue our discussion about posterior predictive distributions. Just like last time, we are going to be talking about data with a binomial likelihood and a beta prior for the parameter pi. But this time, the future sample of interest has a sample size n star bigger, greater than 1. Okay? Let's begin. So, again, just like last time, let's summarize what we know about this problem. Okay? So, the parameter of interest is pi. Our prior distribution is going to be given. We're going to be concentrating on the case where the prior distribution is a beta prior with parameters alpha and beta. Okay? Then we need our likelihood. We know that's going to be the conditional distribution of observing y given a particular value of our parameter pi. So in this case, it's going to be binomial, right? So let me write that down here. Exactly. N star, well, n factorial divided by y factorial times n minus y factorial times pi to the power y times 1 minus pi to the power n minus y. Okay, and we know that that probability mass function applies for values of y 0, 1, 2, up to n, right? N being the sample size of our, initial sample. Okay, so posterior distribution, that's the other thing that we're going to need to carry out statistical inference from a Bayesian perspective. We have to reverse these guys. Now it's the probability of pi given that we have observed our data y, right? And the posterior, right, we know it's going to be a product between well, it's proportional to the product prior times likelihood, right? Okay, so in this case, let me remind you, right? And again, this time I'm going to write things exactly because it's going to be important for us in the near future for what we are about to do. Okay? So we know that the PDF of a beta distribution with parameters alpha and beta is given by the gamma function evaluated at alpha plus beta divided by the gamma function evaluated at alpha and times the gamma function evaluated at beta And then what we have is pi to the power alpha minus 1 and times 1 minus pi to the power beta minus 1. And we know that the support of this PDF is the 0-1 interval. Make sense? Okay, so our posterior, right, is going to be, right, proportional to prior times likelihood. Prior times likelihood so this guy, when we do that product, is proportional to pi to the power alpha plus y minus 1 and times 1 minus pi to the power n minus y plus beta minus 1, right? Okay, so usually what we say is that our posterior distribution, right, has beta with parameters alpha star. Alpha star will be this guy, alpha plus y, and beta star will be n minus y plus beta. Okay? Okay. But now, as we said, the problem that we want to solve, we want to find the probability of getting y star successes in a future sample of size n star. Okay? So in other words, what we want, mathematical notation would be the probability of seeing y star given y. Okay? That's what we want to, that's the question that we want to answer. Okay? So we know that we will be using the definition to answer that question. The definition of predictive posterior distribution. Definition. Okay? So it goes like this. In this particular case, the case of a proportion, will be given by the following integral. The integral from 0 to 1. Just give me a sec. So, as I was saying, it's the probability of y star given y, and it's going to be given by the integral from 0 to 1 of the probability of seeing y star given pi times the posterior distribution. Okay, and we are integrating with respect to pi. Okay, now we know that y star could take on the following values, right? Since we're talking about future sample of size n star, we could observe 0, 1, 2, up to n star successes. Okay? Okay. So, now what we want to do is applying that definition in a more general case. Last time, well, in another video, right, we did this for n star equal to 1. Now we want to extend those ideas. Okay, so that's why I was more careful in writing the expression for our prior and our likelihood, because it will be useful. Okay, so here we go. So using the definition, right? By definition, let me copy paste this, but then I'm going to substitute probability of observing y star successes given a value of pi. So if you think about it, that's your likelihood evaluated at y star, right? That's the probability of observing y successes given a particular value pi. So let me copy paste this. I'm going to substitute here, and instead of a y, I'm going to have a y star, right? And instead of an n, I'm going to have an n star. So y star y star y star y star, and instead of an n, we will have n star, right? N star n star. Make sense? Okay, now here we have, this is just the general formula, right? In this particular case, what we said is, well, the prior that we're going to be considering is a beta, right? And after we do the calculations, we end up with beta posterior, right? So, and the beta posterior has these parameters, alpha star and beta star. Okay? So let me use that expression, and I'm going to write down, instead of an alpha, I'm going to write down an alpha star, instead of a beta, beta star, right? Because it's the posterior, right? But I need the exact expression for what we are about to do. So I know that the posterior, it is also a beta, but with parameters alpha star and beta star. Okay, so let me just substitute that here and change those alphas for alpha stars and betas for beta stars. alpha star, alpha star, alpha star. That's it. We want a beta star here. And we have beta star and beta star. Make sense? Okay, let me place it here in the next line so you can see it entirely. Okay, just substitute. This would be the likelihood, right? The probability of seeing y star successes in a future sample of size n star. This is the posterior distribution, a beta with parameters alpha star and beta star, given that what we are doing here is considering a beta prior, right? So now what we have to do is find that integral. We've done something like this before, but when n star was equal to 1. This is kind of a more general case, but it's going to be similar. Okay, now I want you to note something interesting here. We are integrating with respect to pi. So if we have terms that do not involve pi, those are constants, right? So we're going to pull out those constants out. We're going to pull out those constants, right? So, for instance, this guy here, we could pull that guy out. That constant here, we could pull that out as well. And now what we could do is a little bit of algebra, right? So instead of pi, what we're going to be doing is pi to the power y star times pi to the power alpha star minus 1. Well, we could combine those terms, right? So that's plus, right? So we don't need that one anymore. Let's combine these. Okay? Plus, right? Makes sense? Yeah? And now we don't need this one anymore. So let me use brackets here. And let's make a little change of variables. Let me define something like this. Alpha yeah. Not what I wanted. Alpha tilde. Okay, that's better. Okay, so that guy, I'm going to define alpha tilde as this, y star plus alpha star. Okay, and I'm going to define beta tilde like this. Is going to be n star minus y star plus beta star. Okay. So let alpha tilde be that. Let beta tilde be this. Right. So now let me rewrite that. As you can imagine, what we are trying to do here is we are trying to make it look like a beta. like the kernel of a beta, and then all we need to do is find the right constant, and then that kind of a scary looking integral is just going to be a beautiful one, right? Makes sense? So once we see that, we clearly realize that we are dealing with a beta distribution with parameters alpha tilde and beta tilde, right? So now we go, okay, if I had the right constant, then that integral would be 1. The right constant would be gamma at alpha tilde plus beta tilde divided by gamma evaluated at the new alpha times the gamma function evaluated at the new beta, right? So let me borrow this and make the changes that I need. So that constant, but instead of alpha star, we have this guy here. And this guy here, right? But now you go, hey Al, you're multiplying by this guy and dividing by this guy. So you can't just do that, right? Yeah, you would be right. So what I would need to do in order to do things in a legitimate way is we would need to multiply by the reciprocal of this guy. So if I am multiplying by this, I will be dividing by the same quantity, and since I am dividing by that quantity, I'm going to be multiplying by the same quantity here, and that is just a beautiful 1, right? And once I do that, right, once I do that, clearly this, the integrand here, what's inside that integral, is the probability density function of gamma with parameters alpha tilde and beta tilde. We are integrating over the entire support from 0 to 1, right? So that's going to be a beautiful 1, and then we are only left with these 3 terms. Make sense? Okay, so let me write that down. That then in the end, what we have is that the predictive, the posterior predictive distribution is given just by that product. Because the last one, that integral, is just 1. Okay? Are we good? Finally, just for completeness, let's plug in the values of alpha star and beta star. Well, of alpha tilde and beta tilde, okay? So alpha tilde is this guy, right? Beta, there we are. And this guy here would be y star plus alpha star. Beta tilde would be this guy here, right? Note that when we do the math, y star minus y star, they cancel out. So we only have alpha star plus beta star plus n. Let me write that down like that. Looks nicer. Make sense? Yeah? Okay. And that is going to be valid for y star being equal to 0 or 1 or 2 or n star. Make sense? And that kind of scary looking probability distribution has a special name. It's called a beta binomial distribution. Beta binomial distribution. Okay? Makes sense? So it is a more general version of what we did last time when n star was only equal to 1. Okay? Okay, now let's do an example, okay, to make things more concrete. Example. So how about alpha star, right? And remember that alpha star represents the parameter of our posterior distribution. Alpha star equal to 1, beta star equal to 1, and n star three. Okay, so what we have here is that, okay, we have observed, we have some previous information, we had some previous data. After doing our calculations, we ended up with beta with parameters alpha star equal to 1, beta star equal to 1, and we want to predict what happens. We want to come up with a probability of observing y star successes in a future sample of size 3. Make sense? Okay, so first, what do we have to do first? Well, we have to use the definition, right? So by definition, and then let me go back here to save a little bit of time. We know that the definition is this. And let me also copy that, the possible values of y star. So that's by definition. So in this case, we go, we want that for 0, 1, 2, and 3, because n star is 3, right? We want to do this 4 times. So let's start with the first case. Y star equal to 0. So what's the probability of y star being equal to 0 given pi? So remember, what we are saying is, well, we have a binomial likelihood. What's the probability of observing 0 successes, right? So in that case, we go, oh, no problem. I guess that would be just 3, choose 0, pi to the power of 0 times 1 minus pi cube. So so basically what we have is just failures, 1 minus pi cube. Make sense? Right? If you observed 0 successes, that means that you observed only failures. So when you evaluate the binomial likelihood, you end up with 1 minus pi cube. Make sense? Yeah? Okay. Now, the posterior distribution. So bear in mind that what we have here is beta with parameters alpha star and beta star. So let's plug in. we know that it's going to be the gamma function evaluated at alpha star plus beta star, meaning the gamma function evaluated at 2 divided by the gamma function evaluated at 1 times gamma function evaluated at 1 times pi to the power alpha star minus 1. So 1 minus 1 1 minus 1, and then we have 1 minus pi to the power 1, to the power 1 minus 1. Make sense? Yeah? Okay. But that's just, pi to the power 0, 1 minus pi to the power 0. So we end up only with this. Right? Make sense? So let me copy paste this and let's simplify the expression that we have there. So I will pull out that constant, and then as we pointed out, that's just a 1 and that's just a 1, right? And something more, we could go, well, we could do the calc, or we could do something that Bayesian statisticians do very often, and we have been doing it a lot. Hey, that's the same as pi to the power 1 minus 1, and 3 is the same as 4 minus 1. I recognize that as the kernel of a beta with parameters alpha equal to 1, beta equal to 4. So if I am able to complete that beta, right? So 1 plus 4, gamma at 1, gamma at 4, that's just a constant. So now what I have is a legit probability distribution, and I am integrating over the entire support, so that integral is going to be 1. But since I am multiplying by that constant, I have to divide by the same constant, or in other words, just multiply by the reciprocal. So let me multiply by that, gamma at 1 and gamma at 4. Let me divide by that, right? The gamma function evaluated at 5. Okay, and now let me simplify this. Just 5 and 5. Okay, so as I said, now this turns into a1. And what we have left is these two terms. Now we have to recall the properties of the gamma function. We know that if we evaluate the gamma function at a positive integer n, let's say, the gamma function evaluated at n is the same as n minus 1 factorial. So gamma at 2 is the same as 1 factorial, and 1 factorial is just 1. Gamma at 1 is the same as 0 factorial, and 0 factorial is just 1. So we have 1 over 1, just a beautiful 1. So the gamma function evaluated at 1, 0 factorial, 1, no problem. So now what we have is gamma evaluated at 4 is 3 factorial divided by 4 factorial, right? So 3 factorial divided by 4 factorial, and 3 factorial is just 3 times 2 times 1, which is 6, and 4 factorial is 4 times 3 and so on, right? But we could simplify that as well like this. We could recall that 4 factorial is the same as 4 times 3 factorial, right? 4 times 3 factorial, so these guys cancel out and we end up with a beautiful 1/4. Okay, let me write that down here. Probability that y star equals 0 given y is just 1/4. Okay, makes sense? Let's do one more, and then you can do the others as kind of as an exercise. Okay, so let's do one more. Now let's do y equals 1. Okay, y star equal to 1. Okay, so here we go. The likelihood is the part that is going to change. You guys agree? Because the posterior, that is not going to change, right? So now what we have is our likelihood. We have 3 choose 1. Okay, we have 3 choose 1, which is the same as 3 divided by 1 factorial times 3 minus 1 factorial, right? Agreed? So we have 1 success, because remember, just by the definition, what we want here is the probability of observing y star successes given pi. So if we are going to be observing 1 success, well, we have 3 choose 1 times pi to the power 1. We have 1 success. But if we have 1 success in a series of 3 trials, that means that we had 2 failures, right? And the posterior, that one remains the same, right? That doesn't change. So now we just have to do a little bit of algebra. Well, a little bit of algebra and a little bit of Bayesian tricks, right? Meaning we are going to be doing the same thing that we did before. We're going to try and complete that integral. We're going to try and turn that into a beta. And yeah, that's it. So now what we have is, if you take a look at this, we have, instead of this, pi to the power 1 times pi to the power 1 minus 1, we could just 2 minus 1, and then we get rid of this 1, and then instead of having 1 minus pi squared times 1 minus pi 1 minus 1, how about we do 2 plus 1, 3, right? So we have this. We recognize this as the kernel of beta with parameters alpha is equal to 2, beta is equal to 3. So we complete the integrand. We multiply by the constant that would turn that into a legit beta distribution. Right? But since we're multiplying by that, we have to divide by that. Or, in other words, well, we have to, just multiply by the reciprocal. So let's do that outside that integral. Agreed? So we're multiplying by a1, that is not something against the rules, but now again that integral is just a 1, so we only have these guys left, the three terms outside that integral. And now let's simplify them a little bit. So the gamma function evaluated at 2 is 1 factorial, which is just 1. The gamma function evaluated at 1 is 1 factorial, which is just 1. Same goes for this guy. So it's 1 times 1, right? Gamma function evaluated at 2, 1 factorial, which is just 1. We have here 2 factorial. And we have here 4 factorial. Right? This guy is going to be just 2 factorial, right? So 2 factorial, these guys cancel out. We have 3 factorial divided by 4 factorial, which is the same thing that we had before, which is going to simplify to 1/4. So let me copy and paste this. Okay. So similarly, you could find y star equal to 2 given the probability of y star equal to 2 given y, and the probability of y star equal to 3 given y. And if I remember correctly, what you will see is that the probability of observing 2 successes in a future sample of size 3 would be 1/4, and you would have 1/4 for the remaining one. So 1/4 plus 1/4 plus 1/4 plus 1/4, 1. So it seems to be a legit probability distribution, and we're done. So again, if you have time later today, check that these are the probabilities that you end up with. Okay, so let's summarize, let's recap what we did. So we had data coming from a binomial likelihood, right? Our parameter of interest was pi. We used a beta prior, which yields a beta posterior. The problem that we wanted to solve was this. We want to find the probability of getting y star successes in a future sample of size n star, given that, we have already seen data observations coming from another sample, y. So what we did is just like what we did before. We applied the definition of posterior predictive distribution. In this case is given by that integral, right? But in this case n star was bigger than 1. So first we did this in general for this case. So we ended up with this expression here, the beta binomial. And something that you can also see later, what you can do later is check that if you plug in the values that we have for this example, things will work out, meaning our formula is going to give you these values that we found. Make sense? So in general, what we saw is that we have a formula for this, and the name of that posterior predictive distribution in this particular case has a particular name. It's called the beta binomial distribution. Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.